lectures, we were referring to performance of the aircraft. Normally, aircraft performance, stability and control go together as one subject. Okay, so that's what we are going to start now. And before we go to stability and control, we need some explanations regarding what is equilibrium and what is stability and what is control. And then we'll go to stability under three different axes. One is the longitudinal axis, that's the nose up and down. The other one is the yaw axis, which is left right of the fuselage. And then third is the roll axis, where the wing, right wing goes down and left wing goes down. So these three stability issues are there in an aircraft. In this longitudinal stability, basically that's the nose up and down, is independent of the other two. Meaning you can analyze longitudinal stability by itself, but you cannot analyze directional and roll stability independent of each other because they are coupled. Okay, so we'll go into some detail of that, and we'll also have some small problems in resolving this. I say simple numericals because the actual numericals will be very, very complicated and involved, because you need lots of coefficients, which evaluating them itself is a huge task. And most of these coefficients you can't really get by CFD. Fluid dynamics, computational fluid dynamics, you have to get either by Ventral testing or through flight models. Or there is another option called TATCOM, which is just a collection of coefficients for old aircraft. So when you type in your aircraft parameters, geometric parameters, then what happens is it does some sort of fitting and gives you an initial idea. That apart is very difficult to do. So once we have all the coefficients, then it's a very simple 6 by 6 matrix, for which you have to find the roots. And based on the roots, you decide whether the aircraft is stable or unstable, and if it is unstable, in what modes, and what are the end mode frequencies and all that. So our numericals will be starting from there. So you will have a 6 by 6 matrix based on which you derive all the roots or the eigenvalues of that to tell you what is stable and what's not stable. Not in actually deriving those coefficients, because that involves a different ball game altogether. Okay, so that's the next bunch of classes will be that. So essentially, you'll be able to describe the requirement for studying stability and control. Before that, you define equilibrium, stability, control, and trim, and differentiate between all of them. Stability is a very, very important concept. It's not enough if you have an aircraft with very good performance characteristics. If it's unstable, then the aircraft is not a viable platform. There have been many accidents because of stability. So only when Wright brothers realized the issue about stability and were able to solve it, they were able to fly. Before that, all the aircraft which ever flew were crashing because of stability issues. So this is what I think Oliver Wright wrote in one of his papers. When this one feature, basically balancing and steering, has been worked out, the age of flying machines will have arrived. For all other difficulties are minor importance. So they realize that stability is the crucial part. Once you have that problem addressed or resolved, then the aircraft, other things are minor issues. So another challenging thing is the aircraft, because it's in flight, unlike a road vehicle, has 6 degrees of freedom, 3 translation degrees X, Y, and Z, and 3 rotations over X, Y, and Z axis. But the pilot has only 4 controls, basically elevator, ailerons, rudder. So with these, and the throttle. So with these controls, it's difficult for an aircraft to be, an aircraft with 6 degrees of freedom to be controlled. So this is a statement in Stinton's book. It's not obvious how a pilot with 4 controls manages to fly an aircraft with 6 degrees of freedom. So far what we studied, the performance, it allows us to compute the overall aircraft lift, drag, and moments. Okay, and that is needed, of course. And with well-designed airfoils wings, a careful job of engine and fuselage integration, lift drag ratios of nearly 20 may be achieved. Of course, in a regular aircraft, commercial aircraft, it may be close to about 14, 15. In a glider kind of thing, it can be more. Okay, so it's while lift drag ratio being 20 is good, it's just not enough. So some aircrafts which have predicted L/Ds of 20 have reached much less L/Ds in actual flight. Not because there were errors in computing L/D, because the aircraft became unstable or uncontrollable much before that lift was generated, meaning that angle of attack. So what I'm trying to say here is your aircraft on the paper may give you a lift drag ratio of 20, but even when you're at a much lower angle of attack, less than what an L/D is there, the aircraft may go out of control. So this has, many aircraft have had dismal failures and crashes because of this problem. So it's performance alone is not enough. One has to ensure that stability is built into the aircraft. Most spectacular failures have to do with stability and control rather than performance. It's not as though you don't have enough lift or enough thrust for you to do a stable high degree of turn rate, and that's not enough. But if during the turn the aircraft goes out of control and gets into a spin from which you cannot recover, then there is an issue. You must have seen recent newspaper articles about how an aircraft designed by HAL, I think it's called HAT, new jet trainer, is undergoing spin trials. Spin is where the aircraft gets into a turn and gets into a stall mode together. So it starts spinning downwards. And to recover from a spin, you should have enough capability both in the elevator as well as in the rudder. So if rudder is not designed properly, you cannot get out of spin, and spin used to be called as a deathly spiral, where you just spiral downwards and crash into the ground. So essentially, stable performance alone is not enough. You have to ensure the aircraft is stable and also controllable in the entire flight envelope. So what we do is some basic stability and control issues. The real aircraft issues are that dynamic part of it. We'll only talk about static stability and control. Because dynamic flight dynamics is a very involved course, not really suitable for at undergraduate level. It's more like a MTech level course. But however, even a static stability is crucial. Now you have to ensure this first before you go into the dynamic stability. And even more complex than that is the fact that the aircraft is not a rigid body. Now, so far we have studied where the lift is produced by the wing, and we have ignored the structural deflection of the wing. Basically, we have assumed that the wing is infinitely rigid and it doesn't bend. In reality, wing bends upwards, and if the center of pressure is not properly aligned with the shear axis, I'm sure you have heard of the shear axis in your structures class, then the wing is also twisted. So if the wing is twisted downwards, then the actual angle of attack is lower than what you estimated, and the lift comes down. If the wing is twisted, then the actual angle of attack is higher than what you estimated, and you may have a higher lift. So those things have to be taken into account in real aircraft dynamics or even stability simulations. But we don't go into that. We assume the aircraft is a rigid body. Also that in many of these approximation, we assume it as a point mass, meaning that we don't bother about rotations and other things. Okay, so general discussion on stability and control, and the foundation for you to build on this later during the master's class is what is dealt with here. So basic requirements for static and dynamic stability, control effectiveness are described. Control effectiveness means you have enough control power to bring the aircraft back to whatever direction or equilibrium state you want to do. So enough power in aerodynamics means that your control surface is able to generate enough movement for it to rotate or yaw the aircraft or pitch the aircraft in the direction you want. So for creating enough movement, two things are necessary. One, the control surface should produce the required force. Okay, and also the control surface should be far enough behind the center of gravity for it to be able to generate the moment. Okay, so those things are the ones which say whether your control is effective or not, or whether you have the control authority or the control power required. So, and this brings us to sizing of the control surfaces. And elevator and aileron sizing is okay, but more crucial will be the entire tail sizing, which includes the rudder as well as elevator. Okay, and both of them have certain regulations specified by the International Aviation Authority, which says that this aircraft should be controllable in these following conditions. Okay, we'll discuss that in greater detail, how the vertical rudder is sized and why in some aircraft you have two vertical rudders and why they are tilted outward and all that we will talk about. So in this subject, in this course, you will be answering questions like how far from the CG should the vertical tail and the horizontal tail be located. The ailerons are of course on the wing itself and they are not very far behind the CG, but they are far away from the center of gravity because they are used for generating rolling moment. So the y direction from the center of gravity is more important for ailerons. Okay, not the x direction distance from the center of gravity. Whereas for the vertical tail and the horizontal tail, what is required is how far behind along the longitudinal axis of this they are from the center of gravity to generate the moment. If they are too close, then the moment is not enough for you to control, in which case you have to increase the size of the control surfaces. If they are far enough behind, then it's not an issue. Okay, and what should be the tail areas? So any aerodynamic surface, the C into half rho V square into S. Half rho V square is the dynamic pressure, dynamic velocity, dynamic pressure, which depends on the aircraft's velocity. It is same for all the control surfaces as well as for the wing. So what is important here is the S is the area of that control surface, which is not the same as the wing area. So what should be the size of the tail area, both horizontal and vertical tail, is a question which you need to answer, because that is what tells you what is the control authority your surfaces have. In that, there are two possibilities. One is that can we have a all fixed horizontal tail and vertical tail? No, that's not possible, because you need to give the pilot a control for him to change the pitch up and pitch down using horizontal or horizontal tail, and you should left right yawing through vertical tail, which means there should be certain amount of moving parts, change the local angle of attack. So then we have the question is how much of that horizontal tail and vertical tail should be fixed and how much should be moving parts. You have to apportion them. In just as an aside, if you look at all the passenger planes like Airbus 380 or Boeing 777 and all that, the fuselage length is pretty high. Very long fuselage is 50 meters plus. And the wing is somewhere in 1/3 from the beginning, and they have a long momentum. That's the reason most of the control surfaces, both horizontal and vertical, for these large passenger planes are pretty small compared to the overall size of the aircraft. However, if you look at fighter planes, their length is very small. Even Rafale is only about 12.5 meters. Tejas is about 10 meters. So the distance between the center of gravity and the both vertical and horizontal tail is not high. So you have to compensate the shorter momentum by increased area. And if you keep on increasing the area, then there should be a challenge in structural design. So what is done in combat aircraft is the entire tail is movable. There is no fixed and movable part like in a passenger aircraft. Entire horizontal and vertical tail can be moved in the combat airplanes. And this is because of the shorter momentum. So they have to have a larger area and larger force generation. Sometimes the area is so large that the vertical tail it's split into two, because you cannot have a very long, very high aspect ratio vertical tail there will be problems in fixing it and it will start flexing and all that. So you have two lower aspect ratio vertical tails. Many of these combat airplanes, you see that. Okay, so the Sukhais or MiG-29s or things like that. So that's something which we'll discuss also where and when you going to go into that. So the starting point of our any analysis of aircraft stability and control is the fundamental result of dynamics. Basically, rigid body motion consists of translations and rotations about the center of gravity. So that's something which we need to understand. Okay, and the motion includes 6 degrees of freedom, forward aft motion, vertical plunging, the aircraft can go up and down, forward and aft motion. Then of course lateral translations together with pitch, roll and yaw. Okay, so these are the 6 possible degrees of freedom. We can of course simplify in some cases, like if you're looking at only nose up and nose down, then that becomes just 3 degrees of freedom. When I say nose up, angle of attack increases, lift production is higher, so the aircraft can go up, meaning in the Z direction, and it can also move forward at a higher rate or a slower rate because of that. So you have 3 degrees of freedom. One is 1 rotation and 2 translations. That's one of the simpler cases where we analyze and then find out whether the aircraft is stable or not and how far or how big the horizontal tail should be. However, when we come to the other part, the rolling and yawing, those two are coupled. If the aircraft rolls, it will also yaw, and if it yaws, it will automatically roll. So that is a coupled scenario dealt with later towards the end of the class. Equilibrium is something which all of us have studied in the school itself. But just to recap, in a normal flight, it's usual for the pilot to adjust the controls of the aircraft such that on releasing the controls, it continues to fly at a chosen flight conditions. Like, in a car, it's not necessary to be holding the steering all the time. Even in a bicycle, if you have seen, if you're driving fast enough, you can actually take your hands off the handlebar and the cycle will keep going. There, the stability is caused by the rotating wheels, which act like as a way to stabilize, like gyros. Whereas in an aircraft, that is not there. So in an aircraft, I have to ensure there are certain conditions where the pilot can actually take his hands off and relax, because in an 8-hour flight, you cannot expect any human being to all the time holding the in the controls and then correcting all the time. So there is a condition called trim, where the pilot sets the control surfaces at certain angle. If he's flying level and in one direction, of course, the vertical rudder doesn't come into picture. He will set the elevator at certain angle just to balance out the nose down moment coming from the main lift from the wing. And then once the moments and forces are balanced out, the equilibrium, it's an equilibrium. So this is a condition called trim, and to ensure that the pilot is relieved of the tedium of constantly maintaining the control inputs and doing it all the time, the aircraft is designed for it to have a certain amount of stability after it is trimmed. Okay, so the aircraft is said to be trimmed or in the trim state, where all the forces and the moments, both not only forces but also the moments are trimmed, and if it has a tendency to stay there until there is some disturbance. So all aircraft are equipped with means of presetting or adjusting the datum or trim setting of the primary control surfaces. So once the pilot starts off on the runway, he accelerates towards the takeoff speed. He takes off, climbs to the cruise altitude. Till that time, he's hands-on. He's controlling the aircraft continuously. Once he's at the cruise altitude, he sets the heading, the direction in which he has to fly for next, let's say, 1 hour or 2 hours, depending on the overall flight time. At that time, he sets the control surfaces because it's going to fly at the same altitude, at the same velocity for a certain amount of time. The elevator setting, the throttle setting, everything is fixed. And then he sets minor. He can take his hand off the controls till the next time he is needed to do that. So the ailerons and rudder are basically fitted when you are not tampered with when you're in a level flight, standard level flight. Only when you start rolling or turning or yawing, you need to bring that into account. So in a trimmed normal equilibrium conditions, only elevator comes into play. But anyway, all of them have what are called trim tabs, or smaller pieces of surfaces, smaller surfaces attached to the big surface, which is like a final correction. You must have seen even in your vernier calipers, you move the main thing with your finger and then a small correction towards the end through a thing. Are there. And except very, very small aircraft, like Pushpak or the Tiger Moth, most of the large aircrafts have trim tabs, which the pilot operates. Because they are a small area, the load or the force needed to operate them is not high, and they are used largely to set the trim conditions. Okay, in almost all modern aircraft, when the pilot gets into the mode where he has set the heading and the thrust condition, everything, there is an autopilot switch. Once he switches on the autopilot, it will take care of any minor small disturbances coming in from the atmosphere and things like that. Okay, so almost all aircraft are fitted with, except very small ones, are with adjustable elevator trim, which the pilot uses. Well, you can set a thing in equilibrium, like you can balance a pencil on your hand, but remember it is not stable in the sense that you have to continuously keep moving your hand forward and backward and sideward to keep the pencil balanced on your hand. And that is because it's not a stable scenario. However, if you take a bigger article with a broad enough base and you can balance it on your hand much easier. That's because there is a certain amount of inherent stability in some of the you can say objects. So if they are designed that way, then they'll be stable. So one of the essential requirements for an aircraft, it must be stable for it to remain in equilibrium following trimming. So once the pilot puts it into trim, a small amount of disturbances the aircraft should be able to automatically take care of. Okay, so without the pilots or the autopilot's intervention, meaning that there is some amount of small deviations, it will come back to its trimmed condition. Okay, so thus trimming is concerned with control actions basically required to establish equilibrium with the characteristics required to ensure that the aircraft remains in equilibrium. Okay, but the pilot should have the ability or the authority to move the aircraft from one equilibrium position to another. For example, he has set the direction, the heading and the altitude and the speed for the aircraft. And after about 15-20 minutes, let's say he needs to change the heading a little bit, then he should be able to disturb the equilibrium, take control, and then set the new condition, and on that you again bring it to trim. Okay, so that's the thing. The maintenance of trimmed equilibrium basically requires the correct adjustment of many flight variables in 6 degrees of freedom. Okay, and of course the what I mean by that is that you have to ensure that the lift produced is equal to that of the weight of the aircraft, and the lift produced, as you know, depends on the airspeed, okay, or the Mach number if you are fast enough. Otherwise, its speed is enough. Okay, variable, and it also depends on the CL, meaning the angle of attack, the flight path angle, and of course the airframe configuration, weight, center of gravity, and so many things. Okay, so it's not a very straightforward thing to calculate. The pilots, of course, do it by practice, by muscle memory. It's difficult to actually do numerical calculations for that. And most aircraft, if you have seen, they are symmetrical, or in the sense the left and right half of the aircraft are identical. Okay, except in some odd cases, for example, if there is a multi-engine aircraft and one engine fails, then it is not symmetrical because the thrust production is not symmetrical. Or it's a combat aircraft and the pilot drops the bomb or a missile on one side of the aircraft and not on the other, then there is asymmetry. Otherwise, in most 90% of the cases, or probably even 95% of the cases, the aircraft is symmetrical. Okay, so that means the trimming is needed only for the longitudinal action. Basically, that's the nose up and nose down. Other directions, left, right, and up and down rolling, lateral and direction adjustments are only likely when a symmetry is lost, as I said now, possibly because of an engine failure or a dropped store. So the most crucial thing is the longitudinal trim which is available through elevator deflection. Okay, so summarizing whatever we have done in this, achieving equilibrium and trim is about balancing forces and moments so that they cancel out. Okay, and aircraft have control surfaces in order to alter forces and moments to achieve it. Okay, so when I say you should be able to generate the forces and to cancel out, then I should be able to change the local angle of attack, because the only way force is generated in the aerodynamic surface is through angle of attack. So which means that elevator or all the elevator or the part of the elevator, I should be able to deflect up or down. Okay, up in some cases and down in some cases. Why this is needed, we will get into later detail as to why we need to have this kind of thing, why the tail is behind, and why in some cases there is a canard in the front and all those kind of things. And there's not much you can do for the momentum because it's part of the geometry. So the only thing the pilot has control is in the force generation, which is largely angle of attack of the local control surface. The vertical control surface is just another airfoil, but the axis is different. So again, recapping, a system is in equilibrium if the sum of all forces and moments acting on it at the center of gravity is 0. Okay, and a system is statically stable if when disturbed from equilibrium, it tends to return back to its equilibrium position. So we'll get into this detail later. A system is dynamically stable if given enough time, it actually returns. Okay, I'm sorry, this slide should have been much later, but anyway, let's go to the next set of slides. So now we have to define what is static stability and what is the dynamic stability, and different control surfaces used in order to modify the moments. Okay. So this is what I think this slide came ahead of the beginning part. By definition, which all of us have studied again in the school or even in pre-university, a system is statically stable when disturbed equilibrium, it tends to return back to the equilibrium position. Basically, if you have seen, let's say a bottle of water, you tint it a little bit, the bottle of water comes back to its stable position. But if you tint it too much, it won't come back. Okay, so a system is stable statically when a small disturbance, this is important definition, if the disturbance is small disturbance happens, then it will be able to return back to its position. Just like, a pendulum, if it's suspended downwards, you disturb it a little bit, after a certain oscillation, come back to its position. A system is dynamically stable if given enough time, it actually returns to the equilibrium position, just like a pendulum, which given enough time, it will return back to its position. So, okay, the distinction between these two is what is shown in this figure. Okay, so this has three scenarios. One, the figure A is statically stable because just a ball on a concave surface. You disturb the ball moving out from it, it will roll back to maybe it will roll up and down a little, but eventually it will stop. Okay, so this is called statically stable. Small disturbances, it will come back. Now, section B, the figure B, is what's called statically unstable. It's like it's standing on top of a convex surface. Any small disturbance, the ball will roll away. Okay, remember in both the cases, the force acting is gravity. Okay, when the force is acting is gravity, when you let's say disturb as in figure A or in figure B, the gravitational force you can resolve in two different directions. One is always normal to the surface, the way the reaction force acts. The other one is, different direction. So that direction of the second arrow is what determines whether it is stable or unstable. So the third figure, C, is called a neutral stability. So the ball just displays it, it stays there. It doesn't either come back or off. Okay, so this is the three things which are critical. Okay, so in the question of aircraft, aircraft stability you will have to understand in a way where it kind of correlates with what we have just described in the figure. So with a high degree of stability, so the question would be, why can't we build an aircraft which is very stable? Okay, for example, a huge aircraft carrier or an oil tanker ship is an extremely stable one which can withstand any large size waves and all that. But just imagine trying to turn a large ship. Remember, this is what happened to the Titanic. They were able to identify that they were going to crash towards an iceberg. But the Titanic being so big, they just did not have enough time or the control power to be able to move it out. So intuitively, you understand that stability brings with it an issue of controllability. You will not be able to move it. Just like, it's very difficult to turn a fully loaded lorry as compared to a two-wheeler or a bicycle. So while the aircraft, I would like to have stability, I also like to have certain amount of controllability. Now, this depends on the nature of the aircraft. If it's a passenger aircraft, then the passenger aircrafts are not supposed to be doing any fancy turns and level inverted flights and stuff. So they will have certain amount of stability built in, static stability built in, so that the long flights the pilot is relieved, and as and when some control is needed, the pilot is able to exercise that control. So with additional stability comes the additional difficulty in control. So this sort of relationship between stability and control is found in most mechanical systems. Okay, and the question is, in an aircraft, what is the disturbance? In a road vehicle like a car or a motorbike, the disturbance can come from a road hump or a pothole, where the vehicle suddenly is plunged in downwards or lifted up, and it goes into some oscillations. But in an aircraft, there is no such thing as a pothole or a road hump, but there are what are called gusts. Gusts are small bursts of wind, which are upwards, downwards, or actually in any direction. So when the aircraft is hit by such a gust, the disturbance happens. The angle of attack may be temporarily increased. And it may start rolling. It may start yawing. Anything can happen when it is hit by a gust. So this is the disturbing force in an aircraft. Okay, and static stability, as was stated, creates a force that tends to return the aircraft to its original angle of attack. As you saw in the ball here, in the figure A, when the ball is moved to this position, the gravitational force which is there, one component of it starts moving the ball back to its equilibrium position. Okay, if this happens, then the object is statically stable, meaning when it is disturbed from its equilibrium position, there is a resultant force or a moment which is in the direction of bringing it back to where it was in the beginning. So once this is there, then system is statically stable. That's what I'm trying to say here. A force is created which tends to return the aircraft to its original angle of attack. Okay, and but it is this dynamic stability of the aircraft that determines the way it will return. So in the same the example of a ball on the convex, depending on the concavity of the surface in which the ball is placed, the ball may oscillate over the equilibrium position before it eventually settles down. If the surface is very, very rough and shallow, the ball will very quickly settle back to its equilibrium position. If the surface is smooth and it's very concave, the ball will tend to oscillate over the equilibrium position for a longer time. Okay, it is concerned with the way the restorative force act with regard to time. So the force generated is not constant. Okay, so further you move away from the equilibrium, the restoring force is larger. As you start coming towards the equilibrium, the restoring force reduces and even becomes zero. But because of the momentum gained by the object while moving towards equilibrium, it will continue past the zone equilibrium position, and the restoring force is now reversed. Okay, this happens. The object overshoots the equilibrium position and then comes backwards. Okay, and it's the property which dampens the oscillation set up by the statically stable aircraft. So if the restorative factors, the way the forces act and the magnitude of the restorative forces is what we have to estimate and we have to study when we are talking about stability of the aircraft. And also if the restorative forces is designed to dampen out smoothly so that the aircraft doesn't oscillate too much. That is also part of the design. After a certain amount of damping, the oscillations become smaller and smaller, and eventually return the aircraft to its original position of the whatever angle of attack it was flying. When this happens, the aircraft is both statically and dynamically stable. So this one again reasonably standard figure you must have seen. If this is the equilibrium position, the horizontal line in the figure, let's say this has a positive static and positive dynamic stability, meaning that from this origin, let's say the aircraft is disturbed upwards, then when it starts nose up, the lift produced is larger, so the aircraft starts going up. Once it starts going up, the velocity drops down and the nose down comes, and then the aircraft goes into a nose dive and then recovers again and back over a short period of time. So this time taken for it to return to its equilibrium position depends on the amount of damping it has got. Okay, the next figure is if the damping is not there, let's say undamped, then it'll plunge nose down and then recover and go and continue oscillating. Of course, this is a hypothetical scenario because there is always damping in nature. There is no such thing as no damping. Damping is always there. Just like that, similarly, there is always a case where the negative forces should be there and the system could be unstable. In this case, the last rightmost figure, there is a disturbance and the aircraft goes nose down, and suddenly the restoring force is larger than what is required. The aircraft shoots upwards, it goes higher altitude, then it plunges furthermore, and then it goes very quickly out of control. So if you see here in the first figure, the amplitude in the first when it is disturbed and the amplitude of the next when it recovers and the next disturbed one, you can see the amplitude is reducing continuously. Okay, this is an indication it's a stable aircraft. In this case, the central neutral case, the amplitude away from the equilibrium is same in all the time, so it is neutral. But what you see is more important here. The rightmost one, there was some sound, I don't know what it was. Let's see. I don't know whether somebody is trying to message me or no. Okay, so you can see the peaks from the first part and the second and the third, the peaks are increasing. So this amplitude is continuously increasing with time. Okay, this is an indication that the aircraft is dynamically unstable. Okay, now it's not that this will automatically lead to a crash. The pilot has enough time to recover, provided this amplitude does not double in magnitude in less than, let's say, 300 milliseconds. If the amplitude of the disturbance is doubling in less than 300 milliseconds, the human being cannot control it and the aircraft will go out of control. If the amplitude doubling is, let's say, in 1 second, 2 seconds, the pilot has enough time with training to be able to recover. Okay, what we have discussed is with respect to basically angle of attack, nose up and down, and the similar logic holds for roll and yaw. Okay, so this, if you look at the aircraft figure, which is at the bottom, you have an aircraft flying from left to right, and somewhere at this point where you have this arrow, upward arrow, there is a disturbance which causes the nose to lift up. If the nose of an aircraft lifts up, what actually happens is the angle of attack on the wing is increased. With increasing angle of attack, the lift production is larger than the weight, so the aircraft starts going up. Okay, aircraft starts increasing in altitude, right? And this once this happens, if the aircraft is designed properly, you can see that it will oscillate over time. Once, let's say, it increases in altitude, it's no longer the lift is no longer enough for it to offset the weight, and because with altitude the density has reduced, the speed has reduced, and because forward speed is reduced, both things happen. So the lift produced is less than the weight, so it starts coming down. Okay, so this is what happens, and it comes down over a period of time. If it's statically and dynamically stable, it will settle down to the equilibrium position again. And if it's neutrally stable, it will stay disturbed. If it's statically unstable, then it will diverge straight away, completely out of control. But let's say it's statically stable doesn't automatically mean it's dynamically stable. Okay, it's possible that the aircraft is statically stable, but dynamically unstable in the sense it does has a show a tendency to return towards equilibrium, but it every time overshoots further and further, and the amplitude starts increasing, and that is the dynamically unstable aircraft. So let's do a recap before we go further. An aircraft is stable if it returns to its initial equilibrium flight condition when it is perturbed or disturbed. I did not write disturbed because disturbed could be a large magnitude. Perturbed means a small magnitude disturbance. Okay, meaning that its angle of attack, it was lying at say 3 degrees angle, it's disturbed by half a degree or 1 degree. 3 degrees suddenly becomes 4. If 3 becomes 20, then the aircraft will be out of control. So perturbed means a small disturbance. Okay, so in this case, there are two main types of instability. It's static instability. Uniformly, it will depart away. The aircraft will go away from the equilibrium condition and has no restoring force or no tendency to come back to its equilibrium position. Okay, and then there is an aircraft with dynamic instability. It oscillates about the equilibrium condition with increasing amplitude. Okay, so but initially it shows a tendency to come back, but it overshoots and the amplitude deviation is increasing continuously, and this is dynamically unstable and dynamic instability. So there are two modes of aircraft control. How to control this aircraft? One moves the aircraft between equilibrium states. The other takes the aircraft into non-equilibrium or accelerating state. So equilibrium is fine, but the pilot needs to be able to move it from one equilibrium state to another. That is the control definition. Okay, stable is one definition. Equilibrium is one. These three are different things, so we should be clear. So when I say control, I mean you are deliberately moving the aircraft from one equilibrium state to another equilibrium state with the pilot action and not through external disturbances. It's like, you know, you're going straight on a highway, and then your turn comes and you turn the steering or the handlebar of your two-wheeler to go into whichever direction you are going. Okay, so basically the one moves the aircraft from one equilibrium state to another. That is the control thing, and it can pass through non-equilibrium state, meaning it has to accelerate. For example, we talked about during performance, when the aircraft wants to turn, it rolls, meaning that the aircraft is no longer level flight. The pilot has initiated the action of rolling, which he does by both ailerons and rudder. And once it rolls, the lift production is not enough, so he has to also increase the throttle and or increase the angle of attack. Okay, so there are two conditions for turn rate. This was one of the questions I had asked in the term test. Two limiting conditions are your aircraft does not have the required CL max, or it may have the CL max, but it does not have the required thrust to overcome the drag which comes at the CL max condition. So you can either be limited by CL max or by thrust. Okay, so and because the pilot is deliberately moving from one stable condition to another, control is, you can say, is directly opposed to stability. That's the reason if the aircraft is very, very stable, or any vehicle, by aircraft, even a car or a ship or a train is very, very stable, it's difficult to control it because these two are contradicting each other. So now before we continue further in the stability direction, we have certain assumptions to make. For most flight purposes, airplanes are assumed to be rigid bodies when we are ignoring any structural deformations or bending or twisting, which is part of any actual body. Okay, that always happens. It always bends, twists, everything. But in our analysis at this level, we are going to ignore that. A rigid body has 6 degrees of freedom relative to a special point called center of mass or the center of gravity, whatever you want to call it. Okay, these degrees of freedom are the forward, downward, and sideways translation of the center of mass. So rotations about 3 mutually perpendicular axes passing through the center of mass. Okay, since all airplanes have a plane of symmetry, as I said, the left and the right part are identical, almost identical. The 3 axes are defined with respect to that plane, constitute a reference frame with the origin at the center of mass, as shown in this figure. So if you look at this figure, this is a generic aircraft. So you can also see here pitch and roll and yaw axis mentioned. So pitch is in the y direction axis, where that is OB axis. If you rotate over the OB axis, the aircraft will be nose up or down. If you rotate over the OA axis, it will be rolling, meaning the left wing going down, right wing going up. And if you rotate over the axis perpendicular, which is shown as dashed line OC, then the aircraft is left and right. And the control surfaces are also marked here. The rudder, as you can see here, is moved left and right. The elevator is moved up and down, both sides of the aircraft. Okay, and similarly, ailerons are moved up and down. As I want you to see here that the distance I was talking about, the momentum, the distance from the point O to the horizontal tail and the vertical tail is important. The distance, this distance along the longitudinal axis. Whereas for ailerons, I am interested in the distance between along the wing in the y direction, or you can say OB direction, this distance. That's the reason all the time ailerons are kept at the wing tip, not near the wing root, because you want to have the maximum, what you can say, momentum. Okay, so if I want to be able to control the aircraft enough in pitch up and pitch down, then my elevator should be strong enough, or I mean, big enough to be able to produce the force and farther enough from the center of gravity to generate the moment. If I want to roll the aircraft, my aileron should be powerful enough, and similarly, rudder should be powerful enough. So these are the 6 degrees of freedom of an aircraft, any aircraft, whether it's a fighter plane or a large passenger plane. The logic and the definition is same. So the rotation in pitch is defined to take place about an axis perpendicular to the plane of symmetry, meaning going from the center of gravity towards the wing tip. Okay, and passing through the center of mass. That's called. This is called the pitch axis. As you can see, this is the OB. The arrow marked OB. This is called the pitch axis. So pitch is defined based on this. And another thing I want you to notice here, I'll refer to this later. The wing is almost always fixed as close to the center of mass or center of gravity of the aircraft as possible from the distance from the nose. Of course, it's since it's both left and right wing, it will pass through the center of the longitudinal axis, but you want to place the wing as close to the center of gravity as possible. So that is one of the reasons you ensure that the stability is within limits. Let's say I move the aircraft far behind, then my moment arm is there for the elevator, but the lift which causes the pitching moment also increases. So you want to place the wing as close to the center of gravity of the aircraft as possible. Whereas horizontal tail and the vertical tail, you want to keep it as far away from the center of gravity as possible. And the ailerons as far away from the center of gravity in the y direction as possible. So the change in orientation of the vehicle is such that the rotation is called the pitch angle. Okay, so how much the nose goes up is in how many degrees, that's called the pitch angle, and how fast it goes up and down, that's called the pitch rate. So slowly you start seeing that things becoming more and more complex, in the sense that we are all in most of the performance calculations. We are simply having one angle of attack or one side slip angle, and based on that angle, you plug that angle in the CL alpha curve, you get the CL and you calculate the lift. Okay, now that angle of attack is changing, and it's changing at a different rate, and that's called the pitch rate. So how fast it changes, and that is an important thing. So the moment applied about the airplane, about the pitch axis on the airplane, so I think I need to correct this, on the airplane about the pitch axis is called the pitching moment. Okay, and this is applied through the horizontal tail, either the whole of the horizontal tail or part of the tail. Okay, wait a minute. I'll get out of the Adobe PDF mode and get into the PPT mode, because this is a GIF. In PDF it doesn't show the GIF. Just give me a minute, I'll bring that other one up and then I'll share that again. Okay, are you seeing the slide?
Yes, sir.
Okay, now I'll go into this mode. So now you must be seeing the aircraft model pitching up and down.
Yes, sir.
Okay, and I want you to notice the black parts, which are the control surfaces, which indicate what happens when you deflect the control surface. This is just the pitching motion, which is the nose going up and down, and this is controlled by these two black elevators or the surfaces, which is going up and down. Okay, so this is the motion of pitching. So in order to control the motion of the airplane, the aerodynamic forces should be applied to them at will of the pilot. Either that or the autopilot should be able to operate it. So an elevator is a similar control surface on the horizontal tail or a canard. It could be part of the horizontal tail, or it could be completely a whole of the horizontal plane, a horizontal tail, or in some aircraft, like for example Rafale and even JAS 39, you have a control surface in front of the wing. That's called the canard. So this, both of them, canard or a horizontal elevator, create a pitching moment, which moving the nose either up or down as required, as you saw in the figure. So a pair of control surfaces mounted on the wing and deflected in the opposite directions are called ailerons. And these ailerons generating a rolling movement by which the vehicle can bank either left or right in order to make a turn in that direction. So what you see now is the aileron or the wingtip ailerons going up and down, which will rotate the aircraft. So you can see here wingtips going up and down. So this is the rolling motion. So here the only surfaces moving are the black ones are the ailerons. Other surfaces, control surfaces, are fixed. They are not changing. Okay. Now what happens if you move only the aileron? I'll talk about in greater detail in going down the classes. While when you deflect the aileron up or down, they do generate force to roll the aircraft, but unfortunately they also generate a differential drag on the left and right side being different. Now this means that the aircraft rolls and also starts yawing. That's why I said it's a coupled motion. Anyway, more of that later. So the vertical surface or a rudder is the control surface on the vertical tail that is used for controlling the flight direction by applying a yawing moment on the vehicle. So a left or right deflection of the rudder creates a yawing moment. Okay, moving the nose of the aircraft in the desired direction. Apart from the aerodynamic control surface, the thrust of an airplane's engine can be used as an additional control input. So as I said, there are 4 control inputs the pilot can use: the horizontal tail, the vertical tail, ailerons, and the thrust. So the yawing part, in this you can see the vertical tail alone moving, the other things are not moving. Okay, and in the rudder, the moment you operate the rudder, the aircraft starts yawing. Okay, this is the yawing part of it. You can observe when the aircraft yaws, the sweep angle in one direction reduces and the other side of the wing it increases. For example, in this case, when the left wing moves forward, the sweep angle is less and the right wing sweep angle is more, which means the lift produced is different on the left wing and the right wing. Okay, and which means that it creates a rolling moment. So this is what we mean by saying yawing automatically creates a rolling effect and rolling creates a yawing effect. So if you are studying the stability of it, you need to do a coupled study, which is more complex than the longitudinal one. So the coupled translation and rotational motion of the airplane that lies entirely in the plane of symmetry is termed the longitudinal dynamics. The pitching rotation about the center of mass and the forward and downward mass, and this remaining 2 degrees of freedom, sideways translation, roll and yaw, constitute lateral directional dynamics. So longitudinal dynamics it does not involve lateral, the yawing and rolling. So it is independent. You can study that thing, whereas the other 2, lateral and direction, they are coupled. So longitudinal motion does not generate aerodynamic forces that can excite the other directional instability. So we don't study that. We can study this in isolation. This can be analyzed separately from lateral and directional motion. Similarly, 2 mutually perpendicular axes normal to their pitch axis and roll and lying on the plane of symmetry are termed the roll axis and the yaw axis respectively, as we showed in the earlier case. So a rotation of the aircraft about the roll axis is termed roll, about the yaw axis termed yaw. With the corresponding roll and yaw rates and moments, challenge in an aircraft is that the forces and moments both depend on velocity. Okay, so it's not something which you can divest it from the velocity depending on how fast you are going. And this again is intuitive in the sense that if you're driving a car at a very high speed, a small change in the steering will turn a car into much more rapidly than when you are driving at a lower velocity. Okay, so we'll stop here and we'll continue on Thursday from here. So if you have any questions about today's classwork or on the term test, whatever we had, the questions I had asked in the term test, we can discuss that now before I close. Okay, the floor is now all yours.
Sir?
Yeah.
Sir, can we use the ailerons and the horizontal tail together to generate more roll, sir? Like, will the roll
No.
add up?
No, if you want to add up the roll, then you have to use aileron and the vertical tail. Horizontal tail does not generate a rolling motion in the normal conditions. However, there are cases in very high angle of attack when you are flying. It's possible that at that high angle of attack, unexpected yawing and rolling can happen. They are called divergences. We are not dealing that at this level, but that does happen. Otherwise, if the pilot wants to roll as fast as possible, then he can use both horizontal and vertical, not horizontal, aileron and the rudder.
And sir, you said there will be yawing, like when the aircraft is rolling, there is a yaw generated. Can we use rudder to negate that yaw?
Yes, you have to. You have to. This is called a coordinated turn. Let's say you want to only turn and not yaw. Then the pilot has to use both aileron and the rudder together to be able to do that without yawing. Okay, and similarly, when he wants to just turn yaw, not roll, then he has to also deploy the elevator. So these two always have to be operated together. In you can say in some kind of orchestration is needed when both need to be operated correctly. So of course, it's not that the pilot in the most modern aircraft, the pilot is not directly connected with the control surfaces. He only operates through electronics. So in a, let's say, fighter plane like Tejas or Rafale, there's something called a flight control system, which is just a program. So the pilot just does what he wants to do, and the appropriate deflections and everything are controlled by the computer, onboard computer. So yes, if he wants to only roll, he has to apply the rudder in the other direction to correct the whatever yaw comes in. If he only wants to yaw, he also has to use the elevator to prevent coupling. So only way to decouple is to do a coordinated yaw or a coordinated turn.
Yes, thank you, sir.
So are the assignment questions clear?
Yes, sir.
So assignment, you are free to ask me if you have any doubts. Other than asking me to solve, there of course there are no numericals there. You can ask me clarifications. That is valid. I'm supposed to give you the clarification if you ask me. Okay, if there are no questions, I will. I'm sorry about the initial part. I don't know what happened. Apparently, we have moved towards cloud storage for both Microsoft Teams and Office and everything. I think that's what caused it. So I had to log out and restart my computer, and then it started working. So this problem, I hopefully won't be there from the next class.
Sir,
hello? Yeah.
Sir, can you explain like the fighter jet rolling? How do they like move the ailerons? Or is there any other difference?
No. They have to use the aileron only. Only way you can do the roll is through aileron. Okay, I'll go back to that slide. Maybe then it will be clearer to you.
Like how do they spin, sir?
Spin. Now spin happens when it goes out of control, when the aircraft stalls and when it is rolling. Okay, this is a very, very a dangerous maneuver, and I don't know if I told you guys, I had a chance to sit in a, an old balsa wood and cloth aircraft called Tiger Moth, and in which the pilot demonstrated stalling and loop and 360 roll and all that. But he wanted me to show me spin, and I said I cannot take spin. I mean, I wouldn't have been able to withstand that spin because it goes into a spiraling downwards. So only way to get out of the spin, as the pilot says, is to push the nose down and use the rudder in the opposite direction. So this is the standard rule of thumb: hard opposite rudder and nose down. And if the rudder is big enough and you're able to produce enough moment to get out of that spin, you survive, otherwise you crash. So every aircraft has to be tested for its spin stability, and that's what the HAL is doing now for its advanced jet trainer. Once it is certified that it is able to get into and out of spin, then only it will be given permission to fly. It will be flight worthy. Okay, I think let me share this again. If you see this, can you see this GIF or animation?
Yes, sir.
Okay, so if I move the elevator down a small amount, then what actually happens is that the camber of the wing increases. Once you increase the camber, the lift produced is larger. So once the lift produced is larger on one side of the wing, then it goes into a roll. Okay, and together, if you see one side goes down, the other side goes up. When the other side goes up, locally lift produced is less, this side is more. So together, you are able to increase the rolling moment. Okay, in some odd situation, the pilot can amplify this rolling moment by deploying. There is another surface you see in the front of the elevator, another thing called spoilers. Okay, these are used generally to brake, to slow down the aircraft in flight. Sometimes you can also use them to increase the rolling aspect. And this is not normally done because it kills the lift rather than anything. And how, why this deflection of the aileron causes the yawing moment, I'll be able to discuss in detail later in the following classes, and how this is you can kind of reduce the adverse. So the effect of yaw because of aileron is called adverse yaw. Okay, and that adverse yaw is to a certain extent controllable by different techniques people have used it. So we'll talk about that in the next class.